Hello students. In this chapter solid state, we are continuously discussing that the solids, they have a perfectly disciplined, or I will say perfectly arranged particles. For example, one cation, one anion, one cation, one anion. So this is what we will call as a perfect arrangement of the particles, and such a crystal is called as ideal crystal. So what is an ideal crystal? Where the unit cell will have same arrangement throughout the same lattice point. So what is an ideal crystal? Where the same unit cell will contain the same lattice point throughout the crystal, and this arrangement will be called as ideal arrangement. That means there is no foreign atom or any molecule or any extra ion present in the crystal. Neither the cation nor anion is missing from its side. So in all way it's a perfect arrangement. But such an arrangement, it exists only at 0 Kelvin. And if the temperature changes, especially if the temperature increases or decreases, then there develops imperfections, or what we call as deviation, or also defect. So we can say that no solid is a perfect solid, because it will exist as a perfect solid and ideal crystal only at 0 Kelvin. Above or below it, it will have certain kind of imperfections, it will have certain kind of deviations. Now since that because of temperature these imperfections are developed, these defects are developed, therefore imperfections or defects, they are also called as thermodynamic properties or thermodynamic defects. So this is the topic of today's video, imperfections or defects in solids. So what do you mean by imperfection or defect? It is any deviation from completely ordered arrangement of the particle. So what is the deviation? Either extra cation or anion may be present, or cation or anion may be absent, or any foreign particle will be present. Now there are various types of solid: molecular solid, ionic solid, covalent solid, so on. But we will be discussing these imperfections or defects only for the ionic solids. Okay. Now imperfections or solids, they are of two types. One is point defect and another is line defect. Point defect is the one which arises due to single particle, I will say. It can be either atom, cation or anion. Whereas line defect is the one which arises due to a complete row. So the entire row will show some kind of deviation. In our course, 12th class CBSE course, the line defect is not there, and we have to discuss only about the point defects. So what is a point defect? It is a deviation from the ideal arrangement around a particular point or a particular atom. Now what are the causes of point defect? It may arise due to vacancy defect, or it may arise due to impurity effect. Let us discuss them one by one. Vacancy defect is arises due to either a cation or anion is missing from its site. Since our study is correlated to ionic solids, here I will be discussing with respect to cation and anion. So vacancy defects means either cation or anion is missing. In an ideal crystal, there must be 100 cation and 100 anion. Let's say for example. But due to vacancy defect, it may happen that cation are 100 but anion are 95. So that is what we call as vacancy defect. Let us say this is an arrangement of a crystal where alternate cation and anion are present. Let us say any particular particle is missing from its site. So it will create a vacancy. It will create a hole over there. And as a result of this, the density of the crystal lattice will decrease. Coming to impurity effect, it is also called as interstitial defect. Interstitial site means voids, which we have already seen in our previous video. Now what happens in impurity or interstitial defect? Any foreign particle, it can be either atom, molecule or ion, it enters in the crystal lattice. For example, let us say this is the ideal crystal arrangement, and a particular foreign particle comes and occupies the interstitial site. And since extra particle is there, it will result in increase of density. So these are the causes of point defect. The point defect can be categorized into two types. The one is stoichiometric, that is the point defect present in stoichiometric compounds, and the other one in non-stoichiometric compound. In stoichiometric compound, we can further classify it into Schottky defect and Frenkel defect. Whereas non-stoichiometric, that can be classified further into two types. One is metal excess and another is metal deficient. Now we know metal means cations. The metal always forms cations. So what do you mean by metal excess? Metal excess means either cation will be present extra or there will be the vacancy of anion. Whereas metal deficient will be, that means the cation will be deficient, or we can say anion is in excess. So we have to study all these types in detail with particular examples. So we are going to begin with stoichiometric compounds. So let us discuss stoichiometric compounds. Basically, what do you mean by stoichiometric compounds? In this compound, the ratio of cation and the ratio of anion remains same. That means whatever the ratio of cation and anion is represented in the chemical formula, in the crystal lattice, same number of cation and anion will be present. For example, in NaCl. In NaCl crystal, there will be one sodium cation and one chloride anion. So the ratio of cation and anion will be 1:1. So such compounds are called as stoichiometric compounds. It will show two types of defects that we have already seen: Schottky defect and Frenkel defect. That means when the defect arises in these compounds, the ratio of and cation do not changes. Even there is an imperfection, even there is a defect in the crystal lattice, the ratio of cation and anion do not changes, and therefore we call them as stoichiometric defect. So what is a Schottky defect? In Schottky defect, in a perfectly arranged crystal lattice, one cation is missing from its place as well as one anion is also missing from its place. For example, ideally if there are 50 cation and 50 anion, then when the defect arises, 5 cation will be missing as well as 5 anion will be missing from the given crystal lattice, and therefore overall ratio of cation and anion remains same. Such type of defect is called as Schottky defect. Now what are the causes or the conditions that are responsible for Schottky defect to arise? The Schottky defect arises when there is high coordination number of the crystal lattice. Secondly, when the size of cation is near about equal to size of anion. In that condition, Schottky defect is shown. What is the impact of Schottky defect? Now, since cation and anion both are missing in equal quantity, therefore Schottky defect results in lowering of density. Very important point. Overall, this today's video have lots of questions that can be asked in your board exams. Okay, let us discuss the examples. The examples of compounds which show Schottky defect, they are like sodium chloride, potassium chloride, cesium chloride, silver bromide, etc. Now we know there is a great difference of size between sodium and chlorine, potassium and chlorine, cesium and chlorine. Sodium, potassium and cesium are the elements of group 1 and chlorine is an example, or it is an element from group 17. So there is a huge difference in the size, or due to trends changing in the periodic table, the size of cation becomes almost equal to size of anion. Coming to Frenkel defect. Now what happens in a Frenkel defect? Again here I have represented an ideal crystal. Any particular ion, let's say cation, is missing from its place, but it will occupy some other interstitial site, or it will occupy some other void. So it is not missing from the overall crystal lattice, it will remain in the crystal lattice itself, but it will get dislocated from its place, and therefore Frenkel defect is also called as dislocation effect. So in what conditions a crystal lattice can show Frenkel defect? It must have low coordination number, and the size of anion should be larger than the size of cation. And then only the cation can leave its place and occupy the interstitial site. Because we know the cations, they are smaller than their parent atoms. What is its impact? It do not affect the density because the missing cation is occupying an interstitial site. Examples like silver chloride, zinc sulfide, silver iodide and silver bromide. Now silver bromide, this is the compound which shows both Frenkel defect as well as the Schottky defect. Now why? Because silver bromide, it has coordination number 6, which is neither too small nor too large, as well as the radius ratio of silver cation and bromide ion is intermediate. There is not much difference. As well as we can say the silver cation, they occupies octahedral void, and bromide ion, they occupy tetrahedral void. Now this is the reason why it shows Schottky effect, and the reason behind why it shows Frenkel defect also, because the silver cation, it is very small in size, and therefore it can easily leave its place and can move to other interstitial site, and therefore silver bromide is the compound which shows both Schottky and Frenkel defect. It's an important example. So that was all about the defects in stoichiometric compounds. Now we'll discuss the defects in non-stoichiometric compounds. Basically, what do you mean by non-stoichiometric compounds? The ratio of cation and the ratio of anion, it is not same. And generally the non-stoichiometric defect, it is shown in transition metals. Okay, coming back to this one, let us discuss the example of iron oxide. Iron oxide, as the chemical formula suggests, the ratio of iron and oxygen has to be 1:1. But it is found that iron is present in the amount 0.95 and oxygen is present 1. The ratio of iron ranges from 0.93 to 0.96. The reason, there is a defect. FeO is also known as Gold's fool. Now non-stoichiometric defects, they are of two types. One is metal excess that means the extra cation, and another is metal deficient. That means there is a deficiency of cations. So we'll be beginning with metal excess first. Now whenever I say metal excess, that means the cations are more than the anion, or I will say there are certain anionic vacancies, or there is the deficiency of anion. So we'll try to understand this example here. In a perfectly arranged crystal lattice, suddenly sometimes an anion is missing from its place. You can see in this crystal lattice the cation and anion, they are perfectly arranged alternate. But sometimes due to some reasons the anion is missing from its place, and therefore there exists extra positive charge. A crystal solid has to be neutral. So to maintain the electrical neutrality, the electron gets trapped over here. And this hole is created. This hole is called as F center. This hole is called as F center. The word F is derived from the German word Farben. It means color. So the presence of F center in the crystal lattice gives color to the crystal. As I have told you that F centers, they are responsible for color. So I will say the more number of F center, more will be the intense color. And due to presence of the electron, all those compounds which shows anionic vacancies, or all those compounds which have F center, they are paramagnetic in nature. Let us discuss one example for this. In the crystal lattice of sodium chloride, all the cation and anion, they are very well disciplined arranged. Alternate cation and anion is present. But suppose this solid is heated in presence of, let's say, sodium vapors. That also excess sodium vapor. We know that when the metal is in the gas form, it will form cation very easily. So this excess sodium vapor, they will release an electron and they will form the cation. Now in this crystal lattice, which was already arranged in a disciplined way, there will be changes. The chlorine from here will get attracted towards this sodium cation to form sodium chloride. Similarly, some more chloride from its size, they will leave the place to form to combine with the sodium cation and to form sodium chloride. As a result, what happened? As a result, the hole is created over here, and the electron which was released by sodium, it will come and it will occupy this place. That is what we call as F center. And due to presence of this F center, there exists color. Here are some more examples. The yellow color of sodium chloride is due to when sodium chloride is heated in excess of sodium. Similarly, the violet color of KCl or pink color of lithium chloride is due to when they are heated in excess of metal. Okay, so this is an important example for your board exams, and many a times this question has been repeated depending based on F center or based on the color of the compounds. So that was how anionic vacancy is responsible for color of the compounds. Let us move to cation excess. But before that, all those crystals which shows anionic vacancy defect, they generally shows Schottky defect. Please remember this point. In cation excess, again we'll consider one perfectly arranged crystal lattice. What happens in cation excess is, let's say one particular cation leaves its place and occupies some other interstitial site. A solid has to be electrically neutral, and therefore to neutralize this extra positive charge, an electron enters in some other interstitial site. That is what happens in cation excess. For example, zinc oxide. Zinc oxide when heated, it turns yellow. Zinc oxide when heated, it forms zinc plus 2 and releases 2 electron. So if I consider this compound as a zinc oxide, this will be zinc cation, and these extra electrons will be occupying the interstitial site to maintain the electrical neutrality. Remember, the yellow color of zinc oxide is due to cation excess. Don't write the answer here F center. That is the most common mistake that the students do. Okay, all those solid crystals which shows cation excess defect generally show Frankel defect. Overall, we can say that the metal excess result into the colored crystals as well as it results into N-type semiconductor. Semiconductors you must have studied in your physics. Moving on to metal deficiency defect. Metal deficiency means the number of anion becomes more than the number of cation. So it can be due to cation vacancy or deficiency. That's the first topic that I am going to cover. In this type of defect, in a perfectly arranged crystal lattice, a cation leaves its place or a cation is missing from its place. Obviously, the electrical neutrality has to be maintained. So, to maintain the electrical neutrality, let's say the nearest neighboring cation, it will change its charge. The nearest neighboring cation increases its covalency, and this is how the electrical neutrality is maintained. So, what we have seen? The cation leaves its place or is missing from its place, and to maintain the neutrality, the nearest cation or the nearest particle, it increases its covalency. For example, iron oxide, and due to this cation vacancy or cation deficiency defect, the ratio of iron changes from 0.95 and oxygen remains 1. This ratio can change from 0.93 to 0.96 because some of the iron, they will change their covalency, they will change from plus 2 to plus 3. This is an important example. Moving on to the last defect, anion excess. In anion excess defect, an extra anion enters the crystal lattice. This is a perfectly arranged crystal lattice. Let's say extra anion enters in any of the interstitial site. Now again electrical neutrality has to be maintained. To do that, the nearest particle changes its covalency. So I will say this anion, correct word is extra anion, occupies the interstitial site, and as a result the nearest particle, it changes or it increases the covalency in order to maintain neutrality. For example, cadmium chloride. If the chloride anion is in excess, cadmium changes its covalency. Overall, we can say that the metal deficiency, this defect results into the formation of p-type semiconductor. So this is all about the defects in a given solid. Remember, no solid is a perfect. It can be perfect crystal only at 0 Kelvin. Above or below, it will have imperfections, it will have deviations. So based on this, lot of theory questions can be asked. That's all for the day. Thanks for watching. Have a nice day.